Hello again, Physics 20s. In today's lesson, I'm going to talk about satellites, and more specifically, geostationary satellites moving in a geosynchronous orbit around celestial bodies. And then we're going to derive some mathematical equations for the speed of a satellite at a given orbit, and also the period of revolution of a satellite with respect to one of these celestial bodies. Learning outcomes are to 1. Explain quantitatively planetary and natural and artificial satellite motion using circular motion to approximate elliptical orbits. And then 2. Predict the mass of a celestial body from the orbital data of a satellite in uniform circular motion around the celestial body. We'll do learning outcome 2 in the example problem. To explain the motion of a satellite, I'm going to use a bit of an absurd analogy. On the picture that you see, it's an illustration of the Earth, and at the very top of the Earth, there is this humongous hill, and on top of the humongous hill, you have some kind of projectile launcher. It could be like a cannon. What these dashed lines represents is the trajectory of the projectile when launched at different initial velocities. So for example, if I launched a projectile at a low initial velocity, I would expect my range to not be very big. So my projectile would kind of just get fired and then it would just fall down towards the Earth's surface. If I started to increase my speed that I'm firing the projectile at, I would expect the range to start to get bigger. And if you further increase that, larger initial speed is going to result in a larger range. The way a satellite works is once we get it into whatever orbit it is we want to get it to move at a really, really fast speed. If we can get a satellite to move at a really, really fast speed, what will happen is the satellite will undergo free fall, just like with the other illustrations. But what's happening is it's moving so fast that the position of the satellite with respect to the Earth is not really changing. So the way people sometimes describe the motion of a satellite, and I'll just write this down here, is we can say that a satellite is always free falling. But due to its really high speed, it's never getting closer to the Earth's surface. The reason being is that a really, really high speeds, the speed that you'd need a satellite to maintain an orbit, the satellite is going so fast that its trajectory actually just matches the curvature of the Earth. Therefore, always free falling, but it's never getting closer because, again, its trajectory is just matching the way in which the Earth curves. We're interested in talking about geostationary satellites. Geostationary satellites move with the same orbital period as that of a planet's period of rotation on its axis. I just want to quickly explain that point. What does it mean for period of rotation on its axis? Okay, you may have seen like a globe before where the Earth's axis is actually a little bit tilted. So I'll draw like this axis of the Earth. It's just slightly tilted. Maybe I'm not drawing it properly to scale, but that's okay. If I looked at a point P, and this point P is somewhere in South America, what's going to happen is the Earth is going to spin about this axis. And again, if you had a globe, like you could just take it and you could just spin it. And the period of rotation of a planet on its axis would be the time it takes for example, point P to go all the way around the circle and come back to its starting position. So that would represent the period of rotation on its axis for the Earth. So a geostationary satellite has that exact same period. So the time it takes point P here to go all the way around and come back to this position, we call that T, would be the same time as it would take this geostationary satellite to go all the way around its orbit and then return to its initial position. These two T values would be identical. A geostationary satellite, we refer to it as being in something called geosynchronous orbit, or I suppose you could call it like standard orbit. In the case of a satellite in geosynchronous orbit about the Earth, well, its orbital period would be the same as the period of the Earth's rotation on its axis. And as you know, it takes 24 hours for a point P on the Earth to completely rotate around the axis of the Earth. So the geostationary satellite would have a period of 24 hours. The geostationary satellite, if it's going to be in geosynchronous orbit, needs to be placed in a position that's above the Earth's equator. If it's above the Earth's equator, what will happen is, if you were standing outside and you were looking at one of these satellites, like assume you could actually see it. This is why it's called a geostationary satellite. Whenever you look up into the sky, that satellite would always be at the same position from your perspective. I believe if you put the satellites in a different position that's not above the equator, then the position of the satellite in the sky would, there be some like small oscillations, like based on, I mean, I don't think you could actually like notice it like from one instant to another, but I believe like over the course of like maybe a day or something or a few hours, there might be some slight oscillations in terms of like where the satellite would appear. So as long as you have a satellite that is above the Earth's equator, it will have an orbital period of 24 hours. And if I'm standing on the Earth looking at it, it'll always appear to be in the exact same position in the sky. And again, hence the word geostationary. So from the perspective of someone on the Earth, the satellite seems like it's stationary in the sky. Speed of a satellite. Where I derive an equation, I just want to state what I want some of my variables to be equal to. So we'll say that m1 is the planetary mass and m2 is the satellite mass. And what we're going to do is we're going to derive an equation that is going to tell me if I want to put a satellite in a very specific orbit. And when I say an orbit, I mean the distance from the center of a planet to whatever position above the Earth that I want the satellite to be located. So we're going to derive an equation that tells me what speed is required for a satellite to maintain the orbit that I want. And we're going to derive it by using a free body and mass acceleration diagram. So let's say that we have the Earth, and let's say our satellite's located at the very top. So it's moving in circular motion around the Earth. So if I draw a free body diagram of the satellite, I would have a gravitational force of attraction that's trying to pull the satellite towards the center of the Earth. That's my centripetal force. The direction of my centripetal force is also the direction of your centripetal acceleration, which is always going to be towards the center of the circle. And we'll label it as M2 because we're looking at, again, an FBD MAD of the satellite. The satellite is mass 2. My centripetal acceleration would be downward. To derive an equation of motion, because both vectors FG and AC are pointing down, it makes a lot more sense to make down the positive direction. So we'll apply our circular motion physics principle that tells me the sum of my centripetal forces is mass times the centripetal acceleration. It's not even a sum of forces here. The net centripetal force is just that force of gravity that's acting on the satellite. We'll be more specific about M. So M is the mass of the satellite M2, And the centripetal acceleration also points down in the positive direction, so we'll write down positive AC. I'm going to do a couple of substitutions in the next step. So for FG, I'm going to plug in Newton's universal law of gravitation. And for AC, I'm going to plug in the centripetal acceleration equation that is in terms of the speed. So if I do that, I would then have G m1 m2 over r squared is equal to m2 vc squared over r. What I want to solve for in this equation is vc. Vc is going to represent the speed of the satellite to maintain a specific orbit. Now, there's a couple things that can be simplified in the equation. The first is that the masses cancel off. So it's interesting to note that the speed of a satellite to maintain a specific orbit is not dependent on the mass of the satellite. It cancels off. Another thing that partially cancels off is the r on the right-hand side of the equation and the exponent 2 on the left-hand side. So when I get rid of these things, now I have gm1 over r is equal to vc squared. So to get vc by itself, I then take the square root of both sides, which would give me vc is equal to the square root of gm1 over r. That equation is not on the formula sheet. It is one that you do need to understand how to derive. I just want to point out one thing about the equation. So what's the relationship between your speed of the satellite and the orbit it's in? Well, it would have what I might call an inverse square root relationship with the orbit. Now, we didn't talk about inverse square root as one of our variation types, but we can kind of think of it a little bit as being inverse, which basically means that if, for example, you have like a small orbit, that means that your speed needs to be big. And this should make sense. If we have an orbit that's closer to the Earth's surface, I'd probably have to make my satellite move a lot faster to kind of like counteract the fact that the gravitational force would be a lot larger. If we go to a bigger orbit, we're further away, then the speed of the satellite can be lower because the gravitational force isn't as much of a deterrent in maintaining that I suppose in terms of maintaining that circular orbit. I don't want to call it a deterrent because like you need the gravitational force to go in a circle, but I think just the gravitational force makes it more difficult to go in a circle when you're closer to the Earth's surface. Period of a satellite. Now, just like for the speed of a satellite, the period of a satellite and the speed of a satellite, they do not depend on the mass of the satellite. And again, we showed that on the previous slide because the m2 values cancel off. And we're also going to see it in the equation we derive on this one. Okay, I'm going to write down the equation I just derived. So that was Vc is equal to the square root of gm1 over r. What I'm also going to do is I'm going to write down another equation for the speed of an object that's moving in uniform circular motion. Well, that's the equation we're familiar with off the formula sheet that looks like Vc is equal to 2 pi r divided by t. I'm going to take these two equations and I'm going to set them equal to each other. So I have Vc is equal to Vc. And then that would give me the square root of gm1 over r is equal to 2 pi r over t. So the reason I introduced the second equation, the Vc 2 pi r over t, is because I want to get an equation that has period in it. All right, I need to get t isolated. What I'm going to do, because I have this radical, is for the time being, I'm just going to take the square root of both sides just so I can get rid of that radical. So I'll take square root gm1 over r and square that. And then on the right-hand side, take 2 pi r over t and square that as well. The square of a square root, you're just left with whatever's underneath the square root. Therefore, you'd have gm1 over r is equal to, and on the right-hand side, you have to square every single value. So you'd have 4 pi squared r squared over t squared. And what we want to solve for is we want to solve for the variable t. However, I'm going to not do that quite yet. What I'm going to do is I'm going to manipulate variables around in a certain format. And the way I'm going to do this is, first of all, I'm going to have t squared and the GM1 switch spots. I want to get the t squared up to the top because in order to solve for a variable, it needs to be in the numerator of an equation. Now, if I was solving for t squared, I would then get rid of that r on the left-hand side, but for the time being, I'm going to actually bring the r squared from the other side down to the bottom. What that's going to do is it's going to give me an equation that is t squared over r cubed is equal to 4 pi squared over gm1. Now, this step does not in any way make it easier for me to isolate for t, but I've just done this side step for a moment because it turns out that t squared over r cubed, which is equal to 4 pi squared over capital GM1, is equal to a very important constant, a constant that we're going to represent with a lowercase k. This lowercase k is what we refer to as Kepler's constant. And in the next lesson, we're going to talk about, in fact, the next lesson is going to be the end of the unit. We're going to talk about Kepler's 3 laws of planetary motion. And we're going to make reference to this boxed equation when we actually get into that lesson. So I just kind of made this sidestep right now, just so when I get into the next lesson, I can just quickly make reference to this boxed equation that you see here. But that's not our objective right now. Our objective right now is to determine an equation for t. So the way to do that is let's get that r cubed back up to the other side. And then we want t, not t squared, so take the square root of both sides. If you take the square root of both sides, well, the square root of t squared would just be t. And then the other side of the equation, well, there's a couple things I can take the square root of because they're perfect squares. So the square root of 4 is 2. The square root of pi squared would be pi. And then all the other stuff is not a perfect square. Therefore, we're just going to keep it directly underneath the radical. So I have the square root of r cubed divided by gm1. And once again, just notice what t is dependent on. It is dependent on m1, the mass of the planet, not the mass of the satellite. So both your speed of a satellite and your period of a satellite are independent of the mass of the satellite. Now, what does this equation tell me? Well, this equation tells me, what's the variation type between t and r? It is a direct relationship with the square root of the cube, something funky like that. It's still a direct relationship, which means that if you get r to go up, that's also going to make t go up, which means that the further that you get, the further a satellite is in terms of its orbit from the planet, the longer it's going to take for it to go around the actual planet. Okay, so the moon Titan orbits Saturn with a period of revolution of 15.9 Earth days. And if the mean radius of orbit of Titan is 1.22 times 10 to the 9 meters, I want to calculate the orbital speed of Titan, and I want to calculate the mass of Saturn. Okay, so first of all, let's determine what the actual period is. It tells me the period of the moon Titan is 15.9 Earth days. So that would be t. Let's get this into seconds. That'd be 15.9 days multiplied by. Okay, so let's go from days into hours. We know that there's 24 hours in one day. And then we know there's 3,600 seconds in an hour. Cancel some units off here. Days cancel, hours cancels, and then the period would be let's do 4 significant digits. We have 1.374 times 10 to the 6 seconds. So what we're doing is we're on the Earth and we're observing how the moon Titan is orbiting Saturn, and we're measuring how long it takes for Titan to go around Saturn. And by observing how long it takes for Titan to go around Saturn, we're actually going to be able to figure out what the mass of Saturn, a celestial body, is. Now, first of all, let's calculate what the orbital speed of Saturn is. Now, we have a couple equations we can use to do this. So we have Vc is equal to, well, the one equation I derived, which is G mp over r, or not mp over r. Let's use the correct variable I was using before. So let's say gm1, because we're using m1 for the planet mass. So you have gm1 over r, or we can use the simple equation for the speed of an object in circular motion, which is 2 pi r over t. Now, which equation can we actually use here? Well, we can't use the first equation because we don't know what the mass of Saturn is. We're going to use that equation in part B to get the mass of Saturn, but for the time being, we can't use it. So let's just cross this equation out for the time being. So I'm going to use Vc as 2 pi r over t to calculate the orbital speed of Titan. Plug the numbers in. So you have 2 pi times r, and r, it gives me the mean orbital radius, which is 1.22 times 10 to the 9 meters. We'll talk more about what that means in the next lesson, mean orbital radius. For now, it just means the distance from the center of Saturn to the center of Titan. Okay, so 2 pi r over t. T is 1.374 times 10 to the 6 seconds. And then I get the speed of Titan is, we're going to go to 3 significant digits, and I get 5.58 times 10 to the 3 meters per second. So yes, these satellites do move very, very quickly. They need to move very, very quickly so that they can actually free fall at a rate where they match the curvature of whatever planet they're actually in orbit around. B, now we're going to use that other equation for my circular speed to determine the mass of the celestial bodies. We have G m1 over r. I'm just going to use the equation. I mean, if this was an assignment, that I would show the derivation of the equation because it's not on the formula sheet. Because I just did it in the notes, I'm not going to derive it just right now. Okay, I want to get m1 by itself. So to get m1 by itself, I can't do it right now because it's underneath the radical. Therefore, I'm going to square both sides of the equation. And then this would be Vc squared is equal to G m1 over r. To get m1 by itself, just multiply both sides of the equation by r over g. And then I'd have m1 is equal to r times Vc squared divided by the gravitational constant. Okay, let's plug the numbers in. So this would give me mass 1, which is the mass of Saturn, would then be 1.22 times 10 to the 9 meters, multiplied by Vc, which is 5.58, times 10 to the 3 meters per second, all squared. And divide this by the gravitational constant, which is 6.67, times 10 to the negative 11 newtons times meters squared per kilogram squared. And then to 3 significant digits, we get, oops, not mass 2. We want mass 1 here. Then we get mass 1 is equal to 5.70 times 10 to the 26 kilograms. So that's how we can use the period of a moon around a planet to actually figure out what the mass of that planet is. Okay, so that's it for today's lesson. In the next lesson, we'll talk about Kepler's laws and actually finish up the unit on uniform circular motion and gravitation. And in the meantime, you can complete the assignment called satellites. And I'll talk to you in the next lesson.